Our topic of this video is direct variation. So direct variation is one of the two types of variation that we're going to work with linear relations. So this is a case where the linear relation has the y variable, the dependent y variable, is a constant multiple of the independent x variable. So the same number, you just multiply the x value by a number, and that gives you the respective y value, is what it's stating in general. So we're going to look at that in this section here. So the constant multiple happens to also be the rate of change, which we spoke of in the previous lesson. So that rate of change is the constant number that we multiply x by to get the y value. So the formula in general, okay, so we have this rate of change, but the formula in general is the y value, the dependent value, is equal to m times x, x being our independent value or horizontal value. M is the rate of change. I believe the textbook often uses k, but I'm going to use m because later on we're going to have this put together into a formula that most of your teachers in the future will use called y equals mx plus b, and it'll be the equation of a line. So we're going to stick with the m as our value. So m is the number that we change. That's the number we're multiplying by. Multiply by whatever specific number. So, example, x is 4. We multiply 4 by, maybe our m is 2. 4 times 2 is 8. Y is equal to 8. So, it's just 4 times 2. And then the next pair might be 5. So, if x is 5, y would be 10. 5 times 2. So, when we're working on this, we're also looking at a graph. The graph is going to be linear, and in the case of direct variation, and this is one of the two ways you can tell it's direct variation. One is that it's just a multiple of x, such as the equation here, or it is passing through the origin, the 0, 0 point. So this line here illustrates direct variation because it passes through the origin. So it has to pass through this point here. If it passes through any other point on the y-axis, it is not direct variation. So it has to pass through this point. And if you look, we could even make an equation for this line here. If we find our rate of change, we can pick a point right here. When we go over 1, so our run is plus 1. There's our little triangle of rate of change. And then we're going up 2. So 1 and 2. So the rate of change, which is equal to m in this case, we're using the variable m, which equals rise over run. Rise over run, 2 over 1. Or just 2 if you want to simplify it down. So there is our rate of change. So our equation of this line would be y equals 2x. Whatever x value we have, we multiply it by 2, we should get the respective y value. Let's take a look on the graph and see if that works. So right here, I'm at the value of 2. X is 2. 2 times 2 is 4. And that works. It matches up. It's a little bit off on my graph, but that's because I don't draw the straightest of lines sometimes when I'm trying to line this all up. Let's try one more over here. Let's check with this point. So this is at x is negative 1. Negative 1 times positive 2 is negative 2. So that point works there as well. So there is that constant multiple. Any of the values we want. This one's off the graph. Where is this point here when x is 3? What's this point going to be up here when this line extends? Well, x is 3. 3 times 6. 3 times 6. Or sorry, 2 times 6. 2 times 3 is 6. Get that right one time. So the x value is 3. We multiply it by 2, and we would get 6. So this would be hitting a point here at 6 on the y-axis. Even over here at negative 2. Negative 2 doesn't fit. It's somewhere down below. It doesn't fit on the graph, but the equation tells us that 2 times negative 2 is negative 4. So down here somewhere would be negative 4. That's where that line would intersect here. So this line would come down to a point at negative 4. So we can use the equation to find values that aren't on the graph in this case. So some examples working with this direct variation. Table shows some equivalent weights on Earth and on the Moon. The weights are in newtons, which is a measure of force. So it's important to note when you get in, if you get into physics and some of the later sciences, that when you're working with weight versus mass, if you step on the scale and it says that you weigh 150 pounds, that is misquoted as your weight, but it's your mass. It's your mass on Earth is 50 pounds. You're a mass of 150 pounds. That's the amount of material that you're made up of. But if you were to go to the moon, you step on the scale, you're not going to be 150 pounds anymore. You're actually going to be lighter. If you went to Jupiter and were able to weigh yourself, well, on Jupiter, which probably isn't possible because you'd probably get crushed by the gravity, but you would weigh even more. So your weight is based on the force of gravity pulling down on the mass of your body. So we usually use Earth as our standard and then compare everything to Earth. So the moon is lighter than the Earth, Jupiter is heavier than Earth, and so on. So Earth is generally our standard. So that case in our graph, that makes this our x or dependent variable, because that's our standard variable. That one is what we're using as our base. Generally, you can tell that because the first column is our x or x variable as well. And then that will be our y variable. So the first thing I said was to graph that. So that's why x, y variables. So I can plot these points now on here. So I have 50 on Earth, 8 on the moon. So that would be right here on my graph that I set up. Notice I made my scale. I just went up by 25s on the bottom here, went up by 2s on the side here. You make a scale that fits the graph and space that you have, kind of thing, so you can be somewhat accurate. 116. 116 would be about right here. And then finally 150 and 24. So that's going to be right here. So there's my points on the graph, and then I will use my ruler and connect the dots. And again, you want to try and get your lines, your grid lines, if you're hand drawing these, as straight as you can, because that'll give you an accurate representation here. It's just ever so slightly off 0 because my grid lines aren't perfect. They're a little skewed. But we are hitting 0 here in most approximations. So is this a direct variation is the question that's then asked. Well, yes, the graph is crossing through 0, 0, and it's a line. And again, those were the two pieces that we needed for direct variation. This is direct variation, as it is a line through 0, 0. So it's a line through that origin point, so this would be direct variation. In part B, it says that we want to calculate the rate of change using the graph. So if I look at the graph, I want a rate of change. I got my points already labeled here, so I'm going to make my right triangle. There it is. There's my right triangle between 2 points. Again, I'm picking points that are on the grid lines. I could have picked some other ones in between possibly, but these ones are already labeled. So I'm going to rise here. I'm rising. This would be 8. So 8, 12, 16. From 8 to 16. So each of these squares is 4. So 4, 8. I've risen 8. So plus 8. Looking at my run scale and my horizontal scale, 50, 75, 100. So I'm going from 50 to 100. In this place here, that is plus 50. So my rate of change is equal to the m value, which is 50, or sorry, the rise 8 over the run 50. 8 over 50. That would simplify. 8 over 50 does simplify down. 4 goes into, or sorry, 2 goes into both 8 and 50. Goes into 8 4 times and into 50 twice. So we get 4 over 25. Ignore the randomly appearing black marks as I completely wrote the wrong numbers in and for some reason put 100 instead of 50, which screwed up the next little bit here. So I've had to go back and that's the cut in the video. All right, so that's my rate of change though. 4/25, which is a lot better than the last version that I had that you didn't get to see. So our rate of change is again just the rise over the run, and then I've simplified that down to 4/25. The next part says to write an equation to find the height of an object on the moon, or sorry, the weight of an object on the moon. So I'm going to just use my y equals, and again it's y equals mx, the slope, or sorry, the rate of change times x. So y equals m, which is 4/25 times x, like that. I can also write this as a decimal. Depending on the situation that you're working with, sometimes a decimal is good, sometimes it's bad. In this case here, we get 0.16x as our decimal value. It's going to be okay here, but if we were graphing this, good idea in general though to leave it like this in the rise over run form so that we can use it on the graph again. So going over, we'll finish up. So this was y equals 4/25x. So I'm going to use that formula to solve a couple questions here. The first one, use the equation to find the weight, the moon weight of an object that weighs 15 newtons on Earth. So I'm going to sub the 15 newtons in for the x, the Earth weight. So the moon weight, y, equals 4/25 times 15. And then we we do 4 divided by 25 times 15. That's going to get us 2.4. Okay, so something that is 15 newtons on Earth will only be 2.4 newtons on the moon. In the next case here, what if it was 120 on the Earth? Well, y equals 4/25 times 120. And that, again, 4 divided by 25 times 120 in your calculator will pop out a result of 19.2 newtons. Now in this last case here, it's a slightly different situation. We have y equals 4/25x as our general formula, but this time the 50 is the moon weight, so that's the y value. So this is 50 equals 4/25x. Now we'll want to change this 4/25 to a decimal, which was 0.16x. And now, because we're multiplying x by 0.16, to get rid of it, we just divide both sides by 0.16. So 50 over 0.16. Just going to zoom in a bit on that one because it's getting a little small. And divide, and then, x over 0.16. I just miswrote that. So it was 0.16x over 1.6. So those would cancel. I'm left with x on this side. And then 50 divided by 0.16 is going to be 312.5. So that would be the number of newtons that something 50 newtons on the moon would weigh on Earth. And again, I apologize for the making it smaller than that. It's just I'm running in a room as I, again, wrote the completely wrong numbers in the previous situation. Okay, a couple more questions here with direct variation. So in this next one part here, we have Kenesha is paid $12 an hour. So this is a direct variation because her initial pay would be 0. If she doesn't work, she doesn't get paid. That's 0 hours worked, $0 made. The the origin is where the graph is going to cross for that XY00 point. So we want to write a formula relating her pay to the hours worked. So her pay, the amount she's paid, we'll use Y for how much she's paid, is equal to $12 times the number of hours. So Y equals her pay, X equals her hours. Okay, and so Y equals 12x. And that right there is a direct variation relationship. We have a rate of change of $12 for every hour she works, and that relates to the pay. So how much would she earn in 6 hours? Simple to do. We pop in 6 hours as our X value, and we do 12 times 6, which will give us 72. So she would earn $72 in 6 hours. In the next part here, how long will it take her to earn $96? Well, this is the Y value now. This is her pay. So 96 equals 12x. And again, we're multiplying x by 12 here. We got to get it to the other side to get the x by itself. So we're going to divide both sides by 12. These will cancel out. We get 96 divided by 12, which is 8 equals x. That's it. She's got to work 8 hours to earn $96. The last question here, we're working with a scuba diver. He's descending at 15 meters per minute. So what's the rate of change? Well, 15, but because the diver's descending, the diver's going down, and we'll see this better when we get the graph, but because the diver's going down below the sea level there, that the rate of change is actually be negative 15. So that is our rate of change here. So in this case, the rate of change is negative 15 because we're given the rate here. This is our rate, 15 meters per minute, so negative 15 would be our rate of change. That would be our constant multiple. So when we make an equation to show this, the depth, so if y equals the depth, and x is the time, then y equals negative 15x. That would be our equation. And then if we want to sketch this for for 5 minutes, well, the diver. So I got my chart here. I'm starting it with the axes, so I'm on the positive times. So 0. This would be 2, 4, 6 minutes, and then this could be we're going down by 15 meters per minute. So let's count by maybe 15s here. So negative 15 meters down, negative 30 meters down, negative 45 meters down, negative 60 meters down, negative 75 meters down. So that scale I think would work. This is my y, this is my x-axis. And then if I plot some points, the diver's going to start at 0 meters, at 0 seconds. After 1 minute, the diver will go down 15 meters. And then 2 minutes, we'll be down another 15. After 3 minutes, down another 15. 4 minutes, 5 minutes, and I didn't quite make my graph big enough. Let's extend it a little bit here. That's about the same now, I believe. So, poor planning on my behalf. At 6 minutes, he'll be down here at 75 plus 15, or minus, there's negative 75 plus negative 15 is going to give me negative 90. So the diver will be in 5 minutes. Or sorry, I went extra. I only needed to go 5 minutes. I went too far. That's okay. We made an extra point on there. Doesn't hurt us at all. But there is the chart for the first 6 minutes even. The first 5 minutes would stop right there. So the difference here is that note that the rate of change was negative. So the graph is going to go down. It's going to be a descending graph because the rate of change is a negative value. So when the rate of change is a positive value, like this one here, okay, we had a positive 2, the graph goes up. And this one here, the rate of change was a positive value, the graph goes up to the right. And in this case here, because the rate of change is negative, the graph's going to go down to the right. Okay, so hopefully that kind of gives you some idea of direct variation. And then there's some questions you can practice on the notes page.